Hello, Wharton students. Welcome to Introduction to Data Science course, Cracking Regression. Today, I'm going to give you a basic overview of regression, of a fundamental concept in data science and statistics. Let's start by understanding what regression is. Regression is a statistical method that helps us model and analyze the relationship between one dependent variable and one or more independent variables. In our example, we will be looking at how many hours of study will impact test grades. As you can see, the more you study, the better your grades get. Then, can we draw a straight line that best represents this data? We could draw a line like this, which is a line that best fits our data points, allowing us to make predictions on the test grade based on the hours of study. And this straight line that best represents the data points is called the best fitting line. Simple linear regression is plotting a line that best fits the data points, which allows us to predict y values based on the x values. In this model, the x value is known as independent variable, used to predict the y values. And the y value, referred to as dependent variable, is determined by the x value. So let's think about the scenario where we would like to predict the test grades based on the hours of study. The number of test study hours is the independent variable, which means it's the one that we control and change to see its effect. The test grade is the dependent variable because it depends on how many hours we were spent studying. The more study hours usually lead to better grades. Additionally, m represents the slope, indicating how much the y value changes for a unit change, meaning one change in the x value. In our example, a 2-hour increase in study time raises the grade by 10 points, making the slope of 5. Lastly, y-intercept is the predicted value of y when x is 0. In our scenario, a student who did not study at all is predicted to score 46. So putting all the numbers into the equation gives us y equal to 5x plus 46. And this is the equation of the best fitting line for our scenario. In real-world data, not all points lie exactly on the best fit line like this. There is a difference between predicted value by the best fit line and the actual value due to other factors than the hours of study. For example, this student was sick on test day and performed much worse on the test than he or she was supposed to get. So the residual is the difference between the actual value and the predicted value. As you can see, every data point has its own residual, which denoted as epsilon. So our formula now includes this error term, y equals mx plus b plus epsilon. And the predicted value y hat is given by mx plus b. So our residual, which is epsilon, is y hat minus y. So calculating these residuals for all data points will let us know how well the best fit line predicts the actual value. So for example, let's consider this data point. If a student studies for 6 hours, the predicted grade using our model, y equals to 5x plus 46, will be 76. If the actual grade is 70, the residual is going to be 76 minus 70, which is equal to 6. So we calculate this residual for every data point to access our model's overall performance. And next, the sum of square errors, SSE, measures the total deviation of the responsible values from the fit to response values. It's the sum of the square differences between each observation and the overall mean. So smaller SSE indicates that our model better fits the data. And mean squared error, MSE, measures the average of the square of the errors. That is, average squared difference between estimated values and the actual value, where yi is the actual value and yi hat is the predicted value, and small n is the number of data points. A lower MSE indicates better fit, as it means residuals are smaller on average. Therefore, we have to see the best fitting line that minimizes MSE. Now, let's talk about correlation coefficient, denoted as R. Correlation measures the strength and direction of the linear relationship between two variables. The value of R ranges from -1 to 1. R being 1 indicates a perfect positive linear relationship, and R being -1 indicates a perfect negative relationship, and R being 0 indicates there is no linear relationship. For example, we might see a strong positive correlation between hours of study and test grades, meaning as our study hours increase, so do the test grades. In this case, R value will be closer to 1. In the second case, the R value will be our body weight will decrease as the hours of exercise increases. This is the example of negative linear relationship where R value will be closer to -1. In the last example, there will be no linear relationship between hours of study and the body weight. So therefore, our R value will, in this case, in the last example, will be closer to 0. This is the image that shows how data points might look like depending on the R value. As you can see, the correlation coefficient R is always between the values of 1 and -1. To summarize, regression helps us understand and predict relationship between variables. Simple linear regression involves one predictor and one outcome, while multiple linear regression involves multiple predictors. We introduced the error term to account for deviations from the best fit line and discussed how residuals and mean squared error, MSE, help evaluate the accuracy of our models. We also explored the correlation coefficient R, which measures the strength and direction of the linear relationship between variables. Understanding these concepts allow us to make more informed predictions and better understand the relationship between in our data. I hope you enjoyed our lecture. See you again.